I'm interested in the mathematics of materials, and specifically materials that are made from small particles, so particles on the scale of nanometers to micrometers. That's about a billionth to a millionth of a meter. I'm Miranda Holmes-Cerfon. I'm an associate professor of mathematics in the UBC math department. I'm interested in these particles because they make up a lot of the materials that we see around us. So if you brushed your teeth this morning with toothpaste is made up of sort of particles on these scale. The particles that I'm interested in are noisy. They're sitting in a fluid which jiggles them around, and we can't predict where any one particle will go. There's no one equation we can write down to follow its motion and find out where it goes. So the equations that describe them are fundamentally noisy, and we can only describe a collection of particles statistically, and then we can ask what are the most likely states that they'll assemble into and what are the most likely pathways that they use to assemble into these states. If you want to make a shell to contain a drug or an antibody, how would you get particles to assemble into that shell, and how would you put the drug or the antibody in that shell? I want that shape to be very likely, and I want the particles to assemble into that shape on reasonable timescales. I don't want it to take the lifetime of the universe for that to happen. How can I design these particles so that it's overwhelmingly likely that they will form into this shape? And I take a mathematical approach to study the sort of the shapes that these particles can assemble into, and to understand how particle shape and how just underlying geometrical constraints can sort of control what particles can form into. It's hard to manipulate very small things when you can't reach in with tweezers and just put them where you want.